Welcome to the final section of chapter 12. Let me say beforehand, this is the last section that is relevant for the exam. The remaining stuff, which is the stuff of the last week of lectures, will not be part of the exam. Let me say this explicitly, so this is really everything I'm doing in this section 12.6 is still part of it, but none of the rest, so that you know this is kind of the cut for the exam. Okay, so much for the exam. Now, what are we going to do in this section? So the section has a nice title, the second differential and local extrema of a function. And yeah, we shall basically generalize again stuff from the single variable case that we've seen again about how to decide if some point where the derivative vanishes is a critical point or not. I've prepared a bit, so what we did in the last semester in the single variable calculus case was that we discussed a function defined on an interval from the interval to the real numbers, so just some single variable function which is twice continuously differentiable and which has a point at which the derivative vanishes. We have seen by Fermat's theorem that this is a necessary condition for x0 to be a local maximum or minimum point. And we have seen that then we can use higher derivatives to decide if it's in fact a maximum, minimum, or neither. So, in particular, we have seen that if the second derivative at that point is negative, then it must be a local maximum point, so f has a local maximum in x0. And if the second derivative is positive, then we have a local minimum point. If the second derivative vanishes, we have seen that then we need to study the higher derivatives and can still have a method to tell if it's a maximum, minimum, or not by seeing which is kind of the first non-vanishing derivative in that point in case we have higher differentiability in there. But this is kind of the part that's relevant for what we're going to do now, because we're not going to generalize everything with the higher derivatives, because this would be quite messy and complicated in the higher dimensional setting. We will just restrict on what we can tell from the second derivative about local extrema. So this was the situation before, and the situation we have now is that we have an open subset of Rn, as we did before. We have a map on the open subset, so from the set U to R, which is twice continuously differentiable again. And we have seen the local extrema have as a necessary condition that the gradient vanishes there. So all partial derivatives of f vanish in that point. So if we have such a point which has this property, this is some condition which you can just check. This is just a solution of an equation. Assume we have this set of equations, so assume we have such a point where the gradient is indeed vanishing. Then we want to use the second differential, d2f, in the point x0 to decide if it's a local maximum or minimum. We cannot do this all the time, but we have some properties of the second differential that will then help us to do so. So, but this time, of course, it's a bit more complicated, because here we just needed to compute a number, while here, in fact, the second differential is a different kind of object. Namely, what we've seen, just from the construction, the differentials are multilinear maps. And in this particular case, that we're between a subset of Rn and R, we get that d2f x0, so the second differential of f and x0, is now a map from Rn times Rn, so two vectors as inputs, because the second differential, to R. And we have seen that this is a bilinear form. Okay, and if you don't recall what this is, take a look at the beginning of the previous section. There I have defined this notion. So it's bilinear form, and we need to study this bilinear form in greater detail. But in order to do so, we need to discuss bilinear forms in general. So in this point, I will divide this section into two subsections. The first one is about bilinear forms, where I'm basically doing linear algebra and properties of bilinear forms in general. I will restrict to the kind of absolute minimum of what we will need for discussing things. There's a lot more to be told about bilinear forms, but this is not relevant for us now, so let's not go into detail on this. So in the first part, we will discuss bilinear forms in an abstract way, and then in the second part, as in the second subsection, we will apply these things about bilinear forms to this particular case of the second differential, and really then get to local extrema and also see some examples of that. Okay, so let's start a subsection. This is simply entitled Bilinear Forms. Where we do a bit of linear algebra. So I assume now that you know what a bilinear form is. Again, you can look up in the beginning of section 12.5. And I shall now introduce some properties of bilinear forms that are important. So we have seen one particular case of bilinear forms we have studied in greater detail, namely inner products. Those we have studied a lot, and those are special kinds of bilinear forms. So I've discussed that they are bilinear forms, but they have some properties that a bilinear form does not need to have. And basically, the properties I'm introducing now in this definition are these additional properties that we need for this case. Namely, first of all, so okay, the setting, I only do the things for real vector spaces. You could also generalize this to complex numbers or even to more general fields, I think, but yeah, this is not relevant for us. So let V be a real vector space, and let S from V times V to R be a bilinear form. Okay, so just totally abstractly, I've defined bilinear forms for arbitrary vector spaces in the definition where I introduced it. Part A, S is a symmetric bilinear form if it basically has the same symmetry property that inner products have. If I would have an audience now, I would ask, take a guess what it could be. We just demand that S of xy, or let's do the vector notation, S of VW is the same as S of WV for all V and W in V. Inner products have this property by definition. So yeah, this is, but in general this does not need to hold, and we will see simple examples of bilinear forms which are symmetric or not symmetric in a little bit after this definition. And we have a list of 3 properties which are called definiteness properties. Namely, we have said, first of all, S is positive definite, and this is also something I used when I discussed inner products. If the following holds, and now this is kind of modeling the third property of inner products, S of V comma V is positive for all V in V. This is what we've seen. This is a defining property of inner products, that this is always negative. We define 2 more properties. First of all, this negative definite, and now you can probably tell what this will be. Negative definite if S of V comma V is smaller than 0 for all V in V. Now, how do you find examples of that? It's an easy way to construct such examples. If you take an inner product and just do not discuss the product itself, but minus the inner product, you just put a minus in front, then everything flips the sign. So this would be a negative definite bilinear form. Minus an inner product would still be bilinear. This multiplication by constant doesn't matter. So this would be a case of how to obtain them. And there's a third notion, because here many things might happen, namely the notion of an indefinite bilinear form. This means if both of these things can happen, namely if there are vectors V and W in V, so that S of VV is positive, but S of WW is negative. Okay, of course these last 2 properties do not happen in inner products by definition, so this indefiniteness might occur there. But we will later on see that this also has a nice interpretation. We will basically then study the second differential of a function and then check the definiteness properties there and see that this has also some nice geometric interpretation there. Okay, these are 3 definiteness properties, and before going on, let me first of all rephrase the definition of an inner product, namely basically if you see these things that are modeling and plus the bilinearity, these are, we defined an inner product by being bilinear, having the symmetry property and being positive definite. So an inner product can just be redefined in terms of bilinear forms. Namely, an inner product, let me just write this equality sign and misuse this equality sign at this point. An inner product is the same as a positive definite, definite symmetric bilinear form. I think in the language of that many physicists use, this would be a 2-fold contravariant tensor, if this is the right kind of notation that I use. So this is something that really occurs in physics. For example, I think inertia tensors. So there's inertia is kind of modeled. This is a good mathematical framework to express inertia momentum and so on. But so this I will not go into detail in bilinear forms here simply for time reasons. Okay, so this is the same as an inner product. Now let's see some examples of bilinear forms which are not inner product, or not inner products, and which have these properties or do not have them. And let's see, take a look at some of them. So first of all, I consider 4 different bilinear forms that look almost the same. S1, S2, S3, S4 from R2 times R2 to R. So bilinear forms on R2. And they shall be defined as follows. Sorry about that, I had just produced a notational mess, so I have to repeat my definition. So the first one is very simple. We take x1, y1 and x2, y2 written as coordinates in R2 and just take x1, x2 plus y1, y2. This is the same as, this is the standard inner product. This is precisely the way it was defined, but let me include this here as an example for the sake of completeness. S2 takes the point x1, y1 and x2, y2 and just takes it to minus x1, x2 minus y1, y2, y1, y2. I said before this is minus the inner product, so this would be negative definite in that sense. S3 x1 of x1, y1 and x2, y2 is x1, x2 minus y1, y2. And the final example is very simple. S4 of x1, x2, x1, y1 and x2, y2 is simply x1, x2 without the y's. So all of them are symmetric, and this is an easy computation. This is very easy to see because we just have their multiplication which commutes nicely. So all of them are symmetric, but the definiteness properties are different. S1, as I said before, this is the standard inner product. This is positive definite. Okay, and by the argument I lined out before, S2 is negative definite. Okay, what about S3? S3 is indefinite. And why is that? So if we introduce the same vector twice, we need to get something positive and something negative. And there it's easy to see which ones we can use. If we take S3 of 1, 0, 1, 0, we see that this is 1 times 1 minus 0, so this is 1. But if we take S of 0, 1, 0, 1, this would be 0 minus 1 times 1, so this is minus 1, which means this is indefinite. And S4 is neither of the three. And why is that? If we insert the same vector here, let's just call it xy, and do it in both inputs, this would be just x squared, which is bigger than or equal to 0. But it's not positive, so it could only be positive definite, but it's not positive definite, because if we take, for example, 0, 1 and include it twice, so S4 just maps to the product of the x values, which is just 0. So there is really a point. I made a mistake from the very beginning. I am really sorry about that. For all non-zero. Too bad. Yeah, this is fine, but here in these two assumptions, they need to be non-zero. I'm really sorry. Yeah, this is one of these mistakes that you do when you kind of just forget this one simple thought, and you always have the right thing in mind, but forget to write it down. Sorry, this here, both of them in all cases for all v in v without the 0 vector. Of course, it follows from the bilinearity that as soon as one of the inputs is the 0 vector, it must automatically be 0. But anyway, sorry about that. So here we have found so we've seen it's bigger than or equal to 0, but we found a non-zero vector where this is indeed 0, so this cannot be positive definite. Okay, sorry about that little mistake. Okay, yeah, this was first simple example, and let me do one more simple example of something which is not symmetric, because this was all nice and symmetric here, but there are also simple non-symmetric bilinear forms, and an example would be the following one. Let's take S from R2 times R2 to R, where S of x1, y1, x2, y2 is x1 times y2 minus x2 times y1. So here you can see S is a bilinear form. This is something that is easy to check. I mean, I will leave out the details there because this is really a very simple computation that you can do for yourself. But here it turns out that if you do a computation, it is not symmetric. In fact, you can check that S of v comma w, if you just write this as vectors, is the same as minus S of w v, because of the way these things are built for all v and w in R2. So this is what you also call an alternating bilinear form. So it's really just minus there, but this is not symmetric. In fact, this is a the simplest example that you can get for a construction which is important in physics. In the Hamiltonian mechanics, you make use of so-called sympathetic forms. This is kind of something which was taken from Hamiltonian mathematics, and then someone took all the mathematics out of it and dropped the physics and created the field of symplectic geometry, which is now a field that evolved from this. So we just only keep all the fun, all the mathematics, and drop the physics there. But this is some very simple example of a symplectic form in case you should encounter this notion, but that's not relevant for us now. But here we see that this has this, this is not symmetric. And the question is now, of course, what about the definiteness properties? It's easy to see that it has none of the three, because what happens if you have the same vector in there twice? S of xy, xy. So we would have this, so irrelevant of the index here, we would have x times y minus x times y, which is 0. So if we put 2 in there, it's always 0. For all x, y, and R2, so none of the definiteness properties is satisfied. Okay, so much for examples of that. Now, bilinear forms are as algebraic objects. We haven't studied them so far. We have seen a lot about linear maps and would really like to use what we already know about linear maps in order not to develop a whole new theory for bilinear maps, or bilinear forms in this case. But it turns out you can really associate in a nice way endomorphisms of a vector space with a bilinear form. And this construction shall be carried out next. But let me erase at this point because I will need some more space for this. We now want to describe bilinear forms by endomorphisms, and of course it's not at all obvious how this should go. And the idea is now that we start with a given bilinear form, namely with an inner product. We assume we have an inner product given, so in this theorem, which is then 1260, the assumption is that we have a real vector space with an inner product, or in other words, a Euclidean vector space. So a Euclidean vector space, and we additionally assume that it's finite dimensional. In this case, we can easily handle the finite dimensional Euclidean vector space. And we assume we have a bilinear form on this vector space, which is arbitrary. So this is a positive definite symmetric bilinear form. And we have an arbitrary bilinear form on V. Then the following properties hold. We can kind of put S in a relation with V, S in a relation with the inner product by an endomorphism, namely the following way. There exists an endomorphism F from V to V such that S of xy is the same as the inner product of x with F of y for all x and y in V. So we can just modify this inner product by an endomorphism, roughly spoken, and obtain the bilinear form, and we can always find such an endomorphism. B, S is a symmetric bilinear form if and only if the endomorphism F that pops up here is self-adjoint. Okay, in case you are asking yourselves why we are studying self-adjoint endomorphisms, that's one of the main applications. They appear naturally in the study of symmetric bilinear forms, and they appear naturally in many situations, as I said, about inertia and so on, and we will see that the second differentials are always symmetric bilinear forms. I mean, basically we have already seen this, but then it turns out that you can also represent them by self-adjoint endomorphisms, and we will learn more about this later, but this is kind of where this property pops up. Okay, proof. How to see this? So assume we first fix some element y of v. Then, if we take the map which we get if we take S with the second entry y, so the second vector is y, and the first one is still open, this would then be a map from V to R, and by the bilinearity property, if we fix such an element, it is linear in this component, so this map is linear. So it's linear, it's so an element of the dual space, in other words, of V. So it's such a linear map, and to bring this together with inner products, we had a theorem. We had the Ries representation theorem. The Ries representation theorem now says, so Ries representation theorem, that each such linear map can be written as an inner product with some fixed vector, meaning we can associate some vector v with index y, let me call this, in V, such that S of x, y, so this map evaluated in x, is the same as x, comma, v, y for all x in x. Okay, so y was an arbitrary point, an arbitrary vector in V. And to each such y, we can associate this here for all x in x, such that this holds for all x in x. But this already tells us how the endomorphism must be given. Namely, if we have these vectors, we know they exist, define or put f to be the map from V to V, such that f of y is just this associated vector Vy for each y. Then, by definition, S of x, y is x, comma, f of y for all x, y in V. If I had an audience, my question would now, are we done? Is this already it? The answer is no. There's one thing we need to show. It's not at all obvious if f is linear or not. I've claimed that this f is an endomorphism, so we need to show its linearity. Okay, and to do so, let's make a simple computation for all x and y in V. We need 3 ones, f, y1, y2 in V. We compute the following. If we take the inner product of x with the sum of f of y1 and f of y2, we will in a moment see why this is interesting. This is by the bilinearity of inner products the same as the inner product of x with f of y1 plus the inner product of x with f of y2. So by definition, these are x vy1 plus x vy2. And by definition of these vectors, this is nothing but s of x y1 plus s of x y2. But now we can use again the bilinearity. We have the same entry in the first component, so by bilinearity, this is, so S is bilinear. Therefore, we get that this is S of x y1 plus y2. But this must be, so just by definition, this is the same as the inner product of x with f of y1 plus y2 for all x in V. And so we have now two vectors which have the same property, but the Ries representation theorem said that there is a unique such vector. So this is denoted like this, existence and the shriek here. So there exists a unique such vector. So by uniqueness in the Ries representation theorem, let me just write in Ries, it follows that this and this must be the same. So f of y1 plus y2 is f of y1 plus y2 as an argument. So this is the first part of linearity. Now what remains to show is kind of multiplication with scalars. And this is an analogous computation which I want to skip. So rest is done analogously. So just a simple computation by almost the same method. And this way we show that f is linear, which shows the claim of part A. No box here yet. And for part B, this is basically a one-liner. Namely, let's see if I can get it in one line. So B, so symmetry if and only if map is self-adjoint. So let's do this as a chain of equivalences. So S of xy is S of yx for all x, y in V, if and only if, and now we use the definition of f from part A. This means we have x, comma, f of y must be equal to y, comma, f of x for all x, y in V. But we know the inner product is symmetric, so we can here just reverse the arguments. And this, for all x and y in V. And this equation is precisely self-adjointness. So this is equivalent to that, which shows the claim. Okay, so this is what we've seen so far. Now, we've seen there is this endomorphism here, and we could do a lot of theory now about bilinear forms, endomorphisms, and so on, but unfortunately we don't have the time, so I will not go into detail on that, but instead take a look at the most relevant example for us, namely the case of Rn. So consider the following situation. So let n be an n, and take Rn with the standard inner product. So standard inner product. And we have a bilinear form on Rn. Bilinear form. Now, we've seen that linear maps on Rn are always induced by matrices, or are basically given by multiplication with matrices in that sense. So we can just reformulate this here as a condition for matrices. So by part A, so we find such an endomorphism of Rn, meaning we find a matrix. So there exists some matrix A, which is an n by n matrix, with real entries, of course, such that S of xy is the same as the inner product of x and ay for all x, y in Rn. Okay, and part B, S is a symmetric bilinear form if and only if the endomorphism induced by this matrix here is self-adjoint, but we have seen that this is precisely the case if and only if the matrix is symmetric. So here it's the symmetry in the sense we had before, and we recall the symmetry means the transpose of the matrix is the matrix itself. So symmetry along the diagonal, so to say. Okay, so basically, in part C, one additional thing, we can also compute the coefficients of the matrix. Namely, A is then given as Aij, so these are the entries, these should be the names of the entries of the matrix, where Aij is simply S evaluated on the canonical basis vectors Ei and Ej for all I and j in 1 to n. So once we've got this bilinear form here, we can compute straight away this matrix by just putting in the standard canonical basis vectors. Okay, so proof, and there's not that much to show. So A and B follow from the previous theorem, and our knowledge about the connection between symmetric matrices and self-adjoint endomorphisms. So they follow from theorem 1260. So all that's left to show is this little computation that the coefficients are really given as that. And this is basically also a very simple computation, namely for all I and j between 1 and n, we get the following. S of Ei Ej. So this is, by the definition of A, must be the same as the inner product of Ei with A times Ej. Okay, and a slight repetition of linear algebra. So we know that the first vector here, this is the ith canonical basis vectors, which has zeros everywhere except in the ith position. So this would be the ith entry of the vector. And now, just a reminder of linear algebra, what are the images of the canonical basis vectors on the matrix multiplication? This would be a nice question for the audience, but A times the jth vector from the canonical basis is just the jth column of the matrix. And given as a vector in Rn, so not as a column vector, but just as a tuple of numbers here, the jth column is the one that has A1j, A2j, and so on until we get ANJ. And there we see, just by definition of the inner product, this is just the ith entry of this vector here, which is obviously Aij, which we wanted to show. So this is how we can get this matrix here. Okay, so the idea is now that we want, so we know what symmetry is. So symmetry of the bilinear form means that, the matrix is symmetric, but what about the definiteness properties? We will use them later on. So to show that the bilinear form is positive definite, negative definite, indefinite on Rn, we would like to express this as a property of the matrix. And this is what we will do next, namely, and this is very simple to formulate. Maybe I still don't need that much space for this. So first of all, we just translate the definition from before, namely, so that n in n and a in m in an n by n matrix with entries in R. So A, we say the matrix is positive definite. I'll do this once here. Definite. So what we now do is we take a look at the associated bilinear form, which is then given by, where do we have it? This expression here. And I want to say that this is positive definite as a bilinear form. And this just means inserting the same vector here gives a positive number everywhere. So let's do this. This just means the inner product of x and ax is positive for all x. And now I'm not doing the same mistake again. From Rn without 0. Okay, this is just by translating this notion from the definiteness. The same way we say that it's negative definite if this here is always negative for all x in Rn without 0, and part C, indefiniteness. So A is indefinite, indefinite if there are vectors, or let's say x, y in Rn, such that the corresponding bilinear form is then on some, so that, that's right, this x, ax is positive, but y, ay as the inner product here is negative. Okay, this is now just a translation, so let me erase first and then I summarize this. But so this is of course something, okay, great. So we've just written this definition down again. The idea of something being positive, negative, definite, which might be hard to check, we will see that if we use our knowledge about matrices and what we know about them and our computational powers that we have over the matrices, we can just find out without that many difficulties if a bilinear form represented by some matrix is positive, negative, definite, indefinite, and we can really just compute things, which we will see after I erased. Let me fix as a remark what I've already mentioned. So a matrix is by definition positive, definite, or respectively negative, definite, or indefinite if and only if the induced bilinear form has this property. So this is just by definition. So if and only if the bilinear form S of xy is x, ay is positive definite or negative definite or indefinite. So these cases just correspond to each other. Now, I said that you can now use a bit of linear algebra to really see if a matrix is positive definite, negative definite, or not. And this is what I will summarize in the following theorem. So that n be a natural number and that A be an n by n matrix. Sorry, just had a little mistake. We assume only the case that the matrix is symmetric. Okay, so we will study basically the properties of symmetric bilinear forms. We could say more general things, but this is now fine for the moment. So then A, the matrix A is positive definite if and only if all eigenvalues of the matrix are positive. And this is good news, because for the positive definiteness condition, we would need to check this inequality for all vectors, which could be quite an exhausting job and not that easy. But here, we know how to compute eigenvalues of matrices, characteristic polynomial, check the zeros, and so this amounts again to something we can somehow compute. B, matrix is negative definite if and only if all eigenvalues are negative. And finally, C, A is indefinite if and only if A has a positive and a negative eigenvalue. So if both signs occur and a negative eigenvalue. Okay, so can we really compute the eigenvalues and immediately read off if one of the three is satisfied. Of course, in the same way as for bilinear forms, there are matrices which have neither of the three properties. For example, 0 could be the only eigenvalue, or we had something which has like, I don't know, something positive and 0 as an eigenvalue. So this wouldn't work. But this is a really handy criterion that works in many cases. So first of all, concerning eigenvalues. We have a symmetric matrix. What do we know about symmetric matrices and eigenvalues, I would now ask. There's this big result, the spectral theorem. Namely, by the spectral theorem, which we have seen in chapter, which was the chapter number, I think 8? I don't know the number. But by the spectral theorem, we have seen that every symmetric matrix is diagonalizable. Okay, sorry, that's a mistake. A is diagonalizable, and there exists an orthonormal basis of Rn consisting of eigenvectors. Bn to b1 to bn of eigenvectors of Rn. Okay, let us introduce notation for the eigenvalues that belong to these. So that lambda 1 to lambda n be real numbers such that a times bi is lambda I times bi. Of course, some of these values of the lambda I might coincide, such that this holds for all I. Okay. Now let's do a nice computation. Namely, we want to compute these inner product that we need for the positive definiteness. So the inner product of x and ax, we want to show that the positivity of this product for all x is equivalent to the positivity of all these values of lambda. So let's do this computation. So if we write, that x be some linear combination, so I mean everything is a linear combination of these vectors. So let's write this as sum of I equals 1 to n mu I bi. Then if we insert this, this would be the inner product of the sum I from 1 to n mu I bi, and by the linearity of matrix multiplication or of the map induced by A, this is the sum of I from 1 to n mu I A bi. Okay. Now, a bi is just lambda bi, as we've seen, so this is the same as the inner product of sum from I equals 1 to n, or let's give this another name, let's put this to be j, not to confuse these two. So here we've got the vector, and here we've got the sum j from 1 to n, mu j, lambda j, bj. Okay, and now we can use the bilinearity of inner products. By bilinearity, it's compatible with sums and with scalar multiples. So we can basically pull this sum and these coefficients out of the inner product and do the same thing with this as well. So if we do both of them at the same time, we get that this is the sum. If you don't understand this, just take a look at bilinearity and do this computation by yourself. I'm just dropping the intermediate steps here now. We take this double sum of all the coefficients outside, mu I, mu j, lambda j, and it's left here the inner product of bi and bj. But this basis here was an orthonormal basis, meaning this inner product of the two base vectors is the Kronecker delta, delta ij, 1 or 0. So it's only non-vanishing when the indices are the same, and then the sum becomes the following. Then we get that this is the sum of I to n, mu I squared, lambda I. Okay, this is what we get. So, if this inner product is positive for all x in Rn without 0, this is the case if and only if this expression here is positive for all choices of mu. So the sum from I equals 1 to n mu I squared lambda I, this is positive for all mu 1 to mu n, which is such that not all of them are 0. So the whole thing as a vector is not the 0 vector. But this means, in particular, if just one of them is 1 and the other are 0, we would get that lambda I must be positive for each I. So this shows the one direction. If this holds, then the lambda I must be positive. And of course, it's easy to see if the lambda I are positive, this here is always non-negative, then this will always be positive as well. So there is indeed an equivalence. So this is the case if and only if lambda I is positive for all I between 1 and n. And this is precisely what we wanted to show. And for part B, you could do the same thing here by reversing the inequalities. This should then be negative for all of these. So then you can get that lambda I must all be negative. And because these are non-negative and don't change the sign, this is really an equivalence. So B is shown analogously. So, and for part C, I would like you to consider the lecture notes. This is just a nice computation. With eigenvalues, it's not that complicated, but yeah, this is not too hard. Okay, that's basically everything we need about bilinear maps and bilinear forms and the related constructions. The only thing I want to mention now is that this criterion here, the eigenvalues are positive and negative. There is a particular case in which this takes a very simple form, namely if we're in the two-dimensional setting. And this is something where I have put the proof in the lecture notes, but I don't want to bore you with the details because it's just some very elementary computation. You basically need to study quadratic equations and things, so it's not very complicated, but I want you to know how this works. So let A be a symmetric 2 by 2 matrix, which means we have A, B, and then here this coincides with B again, and we have this which we call C. This shall be a symmetric 2 by 2 matrix. Sorry about that. So there's a simple criterion for each of the three cases mentioned here. So the positivity of eigenvalues, negativity, and the case of a positive and a negative eigenvalues. Since it's symmetric, we know it has two eigenvalues always. So it's a 2 by 2 matrix. It can have at most 2, and since it's diagonalizable, it has 2. But these two might be the same. So yeah, there might be one two not necessarily distinct eigenvalues, but it's diagonalizable. Now, here you can see that in this particular case, if you do a bit of computation about, basically you compute the characteristic polynomial of this matrix, which is not at all complicated, and you do some computations with this polynomial and solutions of quadratic equations. Then you see that A is positive definite if and only if the determinant is positive and the sum of the entries on the diagonal, A plus C, is positive. In the same way, you can see that A is negative definite, if and only if the determinant is positive, and A plus C, the entries on the diagonal, this sum is negative. And for the indefinite case, it's even simpler. A is indefinite if and only if the determinant of A is negative. So these are things that are really easy to compute. For we know determinants of 2 by 2 matrices are really simple. So this is something where we can really easily check if some matrix is positive or negative definite, and which we can really will use then to study kind of the positive indefiniteness of second differentials in what's to come. But this is now a handy criterion. So the proof is in the lecture notes. Okay, that's enough linear algebra for this section and for this course, actually. This was the last bit of linear algebra that we needed, I think. Yeah, should be the last. And now in the next subsection, we will take all of this that we've seen here about positive, negative definiteness and so on, and we'll use this to study local extrema and to apply this here to second differentials. See you in the next subsection.